Okay, so this is Unit 5, Stars and Planets. So now we're on to space, the space section. So this is for both double award and separate science students. If you're on double award, this will be Unit 4. If you're on separates, it's Unit 5 because of the extra unit that we've seen in the last video or last presentation. So what we're looking at here, so we are looking here at the main features of our solar system. We're going to talk a little bit about how we measure distances in space. We're then going to talk about the life cycle of stars and what a Hertzsprung-Russell or a HR diagram is. We're then going to look at the forces within a star at the different stages of its life cycle and where they come from. And then finally, we're going to look at how basically everything was made. So elements heavier than hydrogen and where our solar system came from. Okay, so again, here are a whole bunch of different videos to help you out. If you're watching this on YouTube, they'll be in the description below. If you're watching this or if you've got a presentation, obviously you can just click on them and it will take you to them. Now, when it comes to space, because space is so big, if we just used meters all the time, the numbers would get huge very quickly and would get quite difficult to deal with. So instead, what we have got is a whole bunch of different units in the table here below. Now, you don't need to know the exact values of these in meters, but what I would suggest is that you know what they are and that you're aware of them, so that if you're ever asked to define them, you can do. The only one that I wouldn't worry about so much is the parsec. This one down the bottom here. This one, this is just here for completion, because you might hear it mentioned in things, but we won't use it, so don't worry too much about that one. But the other four there, have a look at them, learn them. Like I said, in terms of the values, I wouldn't worry too much, but it's definitely worthwhile knowing that an AU, average distance between the sun and the earth, light year, the distance light travels in 1 year, because I have seen questions asking you perhaps to calculate what they are. Okay, on to the solar system then. So the solar system as we know it today has one star, the sun, has 8 planets, many moons and many dwarf planets, along with comets and asteroids as well. If you look at this picture here, this is the order of the planets. So we start with the sun not being a planet, but then we have Mercury, Venus, Earth, Mars, our 4 sort of rocky inner planets. And then we have Jupiter and Saturn, gas giants, and then Uranus and Neptune, normally known as ice giants. You can also see here labelled things like Ceres, Pluto, Makemake, Eris. These are dwarf planets, or large, could be large asteroids, a bit in between the two of them. Now comets, as it says here, basically dirty snowballs. They're on highly elliptical orbits, and so there are some that we see, what we call periodic comets, that we will see every so many years. For example, Halley's Comet or Halley's Comet. There are others that we might only see once, and then when they get close to the sun, they get thrown out the solar system, never to be seen again. Likewise then, asteroids. Now asteroids are lumps of rock that were too small to become planets. And most of the asteroids in our solar system are found in a belt between Mars and Jupiter. It's thought that this was a planet that failed to form and was basically pulled apart by Jupiter's gravity. Okay, so on to the life cycle of a star. So all stars are big balls of gas. And basically they have been formed by gravity pulling the gas close enough to start fusion. So all they start off as a protostar, and then gravity pulls them in, and all of a sudden we get fusion starting. When they get to that point, they become a main sequence star. At this point, fusion of hydrogen to helium is going, and this causes a radiation pressure, which causes the star to gain in size slightly, meaning that we've now got this balanced main sequence star. This is where the sun is currently. Now, the next stage depends on the mass of the sun, or the mass of the star. If it's a light star, so like up to 8 solar masses, then what happens eventually is it runs out of hydrogen to fuse, and so helium fusion starts. When helium fusion starts, this creates more radiation pressure, and the star itself swells up. As it swells, it cools, and it becomes what's known as a red giant. As a red giant, it will stay here for a little bit, or stay here for a long time, depending on how big it is. But eventually, it will run out of helium, and our star will then slowly start to die. And basically what that means is fusion stops, and as it stops, there's one last hurrah, and it blows off like the outside layer, and we end up with a white dwarf, which is basically the core of the star cooling down as no longer fusion is happening. Now, if it's a heavy star, instead of that red giant, we get a red supergiant. But it's the same process. Hydrogen fusion stopped, helium fusion has started, but this time, rather than just being helium fusion, we then get lithium fusion, and we get all the elements basically up to iron being made, until eventually all the star is left is iron, with some other bits left around it, but a lot of iron inside, and you can no longer do any fusion and release energy. This is where the star will then explode, and this is called a supernova. It's a massive explosion that is, so bright we would probably see the next supernova, would see it probably from Earth during the daytime, be brighter than our sun. And then after that, it will either become a black hole or a neutron star. So the heavier stars become a black hole. The core is so crushed by gravity that not even light can escape it. Or we get a neutron star where the core is still really dense and about the same density as neutrons. The animation that's going on below me is showing this in a bit more detail. So HR diagrams are a graphical way of showing the stages of a star's life cycle. Okay, and you have brightness on the y-axis, or sometimes luminosity, but for us it's the same thing. And then on the x-axis you have temperature in descending order. The reason why it's in descending order is initially when this diagram was put together, that was all to do with the wavelength of light that the star puts out. And basically the hotter the star, the shorter the wavelength of light it puts out. Now the key 3 main regions that you need to know are labelled on this HR diagram. So you have the main sequence going across the middle, you have the giants and the supergiants in the top right, and the dwarves in the bottom left. Now as a star evolves, goes through that life cycle, it moves around. So this is a typical sequence of something like our sun. Now stars increase in brightness in 2 ways. Either they increase in size, which means they have more surface area emitting more light, or they increase in temperature. Okay, and so this is how stars can change on the luminosity scale. So something like our sun, when it becomes a red giant, will be brighter because it's bigger, but it will have cooled down. When it becomes a white dwarf, it will get hotter, but because of that decrease in size, it will appear dimmer. Okay, so that's just something to bear in mind. Okay, now on to the birth of our solar system then. So our solar system was created by the death of a very large star, by the supernova from a very large star. Because all elements heavier than iron on the periodic table are only ever made in a supernova. So what happened then? So this big supernova has left this large cloud of dust, which we call a nebula. Okay, now the centre of this nebula coalesced into the sun. Basically, gravity pulled it together, became the sun. Now because this cloud of dust was spinning, what that means is, as if you spin something, the lighter parts get thrown to the edges first and the heavier parts stay in the middle. So this is why, well, we think this has happened due to the fact that we have our gas giants on the outside and our heavier rocky planets in the middle of our solar system. Now, slowly over time, gravity pulls those dust particles together to form protoplanets. Those protoplanets slowly grew in size as they orbited and absorbed all the dust that was in the path and cleared their orbital neighborhood, so basically the path of their orbit. And eventually, solar system as we know it today was formed. Now, how do we know all this? Basically, this is all based on predictions from observations. So going, well, how could this have happened? Yeah, that makes sense from what we can see. This is our best theory and could well change based on if we find further evidence. Okay, so over to you then. So here are the questions for you to do. Remember, if you're watching this on YouTube, the link to these will be in the description below. If you've got this as a PowerPoint, stop the presentation now, double click on this page. It should open as a PDF if you're viewing this in PowerPoint, not through a web browser. And when you're ready to for me to go through the answers, either restart the presentation or restart the video if that's where you are watching this on YouTube. All right, so see you in a minute.
Now we're going to look at these questions, the stars and planets questions. So again, hopefully you've already had an attempt at these before watching this video, and we'll go through these answers. So on to this question. Solar system was formed by the collapse of a cloud of gas. Oops, so get a pen tool. Of gas and hydrogen. Gas and hydrogen? No, can't have gas and hydrogen. That's the same thing. Gas and dust. Okay, so the table below shows some information about our solar system. So we've got lots of information. Describe how the temperature of the planet depends upon the distance from the sun. So if we look at the temperature, generally, apart from Venus, okay, and yeah, just Venus in this pattern, temperature drops as distance increases. Now, it's important here that you put both of these bits in, because it just says depends on the distance. Doesn't say in the question, which they quite often do, how does the temperature change as the distance increases? So you've got to say the right thing in here. Okay, and one that doesn't follow that pattern is Venus. Venus is too hot. Asteroid belt, hopefully you know, is between Mars and Jupiter. So you've just got to put a temperature that's between Mars's and Jupiter's. So I don't know, minus 100. And an orbital time in years that's somewhere between Mars and Jupiter as well. So I don't know, 5. It is suggested that the greater the mass of the planet, the more moons that will orbit around it. Explain whether this data agrees with this suggestion. Well, the big obvious one is that Mars, 2 moons, Earth, 1 moon, and the mass of Earth is greater than the mass of Mars. So, doesn't agree. So to get the marks here, basically it's 1 pointing out the mass, 1 pointing out the moons. You could pick any 2 relevant planets, but make sure you put in there, again, doesn't agree, to make sure you get both marks. Okay, so on to the 2019 paper. So we've got a star similar mass to our sun. So we go protostar, main sequence, red giant, white dwarf. And if it's more massive than our sun, then we're going to go protostar, main sequence. We're going to go red supergiant, supernova, and then what we're left with is we're left with neutron star. One mark for each of those being correct. Okay, main sequence star is stable because they're equal, so we have to underline the word equal. Stars generate their energy by the fusion of increasingly heavier elements. In the final stages, some heavy elements are ejected when the star becomes a supernova, and these collapse to form a solar system. And again, one mark for getting each of those correct. Right, so on to the way they'd have asked these on the separate science papers. So let's have a look. Complete the phrase below about the sun. So the sun produces heat by fusing, underline hydrogen to make helium. And it's stable because they're balanced, those forces. Compare the main stages in the life cycle of the sun with those much more massive stars. So for me, this is a classic case where I don't need to write lots and lots to hit all the marking points. And if anything, because you're comparing, a diagram would do. We only want the stages. So we could start with the common part. And the common part is that we're both going to have our nebula. Let's write this down better. So the common part is that we have a nebula. It's a nebula. Whoops. Okay, which is going to be cloud of dust and gas. Then we're going to have a protostar. Okay, and then we're going to have the main sequence. So that's the common bit for both. Okay, then if we go down the sun route, so if we make this for the sun, we then have red giant and we have white dwarf. If we go for the heavier one, we have red supergiant. And then we have supernova. And then depending on whether it's really heavy or not quite so heavy, we'll have a neutron star or a black hole. Okay, and so for me, that compares them. You don't need to put in all the fancy words. You might lose a mark because you've not used all the words. But that's 5 out of 6. That's way more than most people will get on that question. Job done. Okay, right. So we're on to Hertzsprung and Russell diagrams, gives us some information about them. And so we're asked about speaker. Okay, let me just bring up the right mark scheme here. What question is this? This is question 3. Would help if I had the right mark scheme. way to go. Here we have. Right. So, explain. Speaker is a very blue star on the main sequence, approximately 10 times the mass. Explain why it's stable. So it's in the main sequence. So this means that radiation pressure. Really can't spell this morning. Radiation pressure and gravity are balanced. Okay, and it's 1 mark for naming the forces, 1 mark for saying balanced. Now, it's 261 light years from Earth. What does that mean? Well, it takes light 261 years to cover the distance. Okay, so the Sun is also in the main sequence. It's a yellow dwarf star. Explain in terms of forces the reactions within the Sun and the properties shown on the HR diagram, how the Sun will change during the remainder of its life cycle. So, the remainder of its life cycle, let's do that first. The remainder of the life cycle is going to go red dwarf, and then it's going to become a white giant. A white giant. We've got these completely the wrong way round. A red giant, and a white dwarf. Okay, so what does that mean? Well, it means that it's going to be brighter but cooler, and then become dimmer but hotter. Okay, now in terms of what else have we got? The reactions. So we'll talk about the reactions. Okay, well, to become a red giant, H fusion stops and helium fusion starts. Okay, and that's during the red giant phase. When it's a white dwarf, fusion stops. Okay, and now we want to talk about the forces. So it says there in terms of forces and reactions, properties. So we then want to say that as a red giant, radiation pressure is greater than gravity. So star, not star expands. And as a white dwarf, there is no radiation pressure, or very little, so gravity is greater than the radiation pressure, so star shrinks. You could also say that at the end of the red giant phase, outward forces blow outer layers, let's just scroll that up slightly, outer layers away from star. So if you have all that, you're going to get your 6 marks again. Again, probably only 5 because of the way I've written it, but that's close enough for us. Okay, so higher 2019. Oh, another QER question. We seem to like their QER questions. So explain in terms of forces a nuclear fusion, the life cycle of a high mass star, from its position of the main sequence to its death. Okay, so the same idea here. When we're on the main sequence, gravity balances radiation pressure. Now, I'd suggest you write out radiation pressure in full, but for now we're doing that. Then we're going to swell to a red supergiant. Why? Well, because radiation pressure is greater than gravity. Okay, then we're going to go into a supernova and we're going to collapse. Let's put these in swell, collapse. Why do we go from this? Well, that's because gravity is greater than radiation pressure. Okay, and then we're going to become a black hole or a neutron star. Due to gravity, basically pulling it all in. Okay, and we need to talk about the fusion. So remember that when we're talking about the fusion, when we're on the main sequence, we're going to have hydrogen to helium fusion. Okay, that's main sequence. Main sequence, when we're a red giant, we're going to have helium and upwards. Fusion. And eventually in the supernova we will create heavy elements, some along those lines, or heavier than creates, let's change that slightly, creates heavier than iron elements. So anything heavier than iron, that was created in a supernova. Right, the number of planets in our solar system totals 8. Briefly outline the difference between the structure of the inner and outer 4 planets. Okay, so inner 4, our inner are rocky, the outer are gas giants, so they're gaseous. Okay, and how do they form? Well, during formation, rocks stayed nearer the sun. Gaseous substances gathered further away. Okay, so Separate Science 2018 now. Okay, so 1982, first detected first exoplanet, found loads since. Here's some information. So, statements: 4 stars have the same mass. 2 do, but not 4. Light travelling from Kepler 90 takes the longest time to reach the Earth. Yeah, it's got the highest distance, so that's going to be fine. The range of star temperatures is 5060. Okay. Hotter stars have more planets in orbit around them. Well, the hottest star here is Kepler 90, and that's got 7. Well, the sun's cooler, so that's not right. Star HR 8832 is double the distance of star HD 4307. No, it's half the distance, so the range one must be the one that's correct without doing the maths, because the others are wrong. State 2 reasons, using evidence from Table 1, why scientists predict that star Kepler 11 is most likely to have a solar system similar to ours. So, it's got the same mass and a similar temperature. Same mass, similar temperature. It's not the same temperature, they're not exactly the same number, but it's a similar temperature, they're very close. Yeah, and those are the two that we're interested in. Okay, exoplanets can't be detected by looking directly, because they don't give out their own light. Okay, why does the detected light intensity decrease during the transit? Well, because the planet blocks some of the light. Okay, calculate the orbit time in days. So what you want is, it's the gap between these two. So I would pick, so if you look here, we go from 0 to 150, and we get 2 in that. So we go 75 days. Yeah, if you look, we've got 0, something that's going to be difficult to read. Next one's at 150, so 75 days is close enough for us. Pupil suggests that there may be 2. Yeah, because you've got that one there. So we have the smaller dip. Yeah, the smaller dip, that's what we want to talk about. During the transit, some of the light is absorbed. How the absorption spectrum arises. So this technically is the next section, but we'll talk about it here. The gases have absorbed, or gases absorb, some light for 1 mark, and different gases absorb different wavelengths. Yeah, so that's how they arise. Gas absorbs some light. And how can it be used? Well, different gases absorb different wavelengths. Okay, continuing on. Kepler 11. Kepler 11 shows data, so it shows the data collected for all the exoplanets in orbit. They are listed in order of increasing distance. Compare the trend in the data with the orbit radius around Kepler 11 to the planets in our solar system where Venus is the hottest. Okay, so generally, both systems, okay, temperature decreases with distance, for 1 mark. The second one is for basically saying, but in our solar system, Venus is the second planet. So it doesn't quite fit the pattern. Yeah, but in our solar system, Venus is the second planet, but is the hottest. Okay, then it asks us to complete the table using this graph. So we come up from 46.7 and we come across and we get to about there. So because it's a bit of a curve, pretty tricky to do, they allow you a range, but it's roughly 0.25 AU. Oh, another Hertzsprung-Russell diagram. So tick the boxes next to the 3 correct statements about the stars shown in the Hertzsprung-Russell diagram. The larger the mass in the main sequence, the longer the star's lifetime. Well, we can't tell. Oh, yeah, we can. We got lifetime. No, that's not right. The largest supergiant is Betelgeuse. Yeah, because it's the one that's the highest up on those lines. Good. The radius of a white dwarf is approximately 100 times smaller than the Sun. So if we look here, 10 to the minus 2 is 100 times, so yes. The hottest star is Beta Centauri. Yeah, because it's the one most to the left. Good. Centauri A. No, can't be very similar to our Sun. And the redder a star, the hotter is wrong. So it's those 3, 2, 3, and 4. It is claimed that as our Sun leaves the main sequence, its surface temperature will increase in the next stage of its life and then decrease as it enters the last stage. Explain whether you agree with this statement. Your answer should include data. Well, currently, the temperature is roughly 5,000 Kelvin for the Sun. In fact, they want 5,500. Okay, for a red giant, the temperature will go down to about 3,000 to 5,000 Kelvin. Yeah, if you look at the graph, the red giants are in this down here. So in this range, 3,000 to 5,000 Kelvin. Okay, when it's a white dwarf, the temperature for white dwarfs, let's have a look, is in this range here, which is 6,000 to about 31,000. Okay, and there's 3 marks for including that, but we better put in that we disagree as well, just to tick that box. Yeah, so we've got the data that basically currently with that, then we're going to cool, then we're going to heat up. They've got it the wrong way around, so we disagree. Explain in terms of forces the changes our Sun will undergo as it leaves the main sequence until it reaches the end of its life. So initially, radiation pressure becomes greater than gravity. So it will expand into a red giant. And then at the final stage, then gravity will be greater than radiation pressure, so contracts to white dwarf. Explain how the life cycle of a star contributed to the origins of our solar system. Well, during a supernova, of a large star, material or heavy elements returned into space, and our solar system came from the collapse of the cloud of dust from such an event. Yeah, so basically our solar system was formed from the leftovers of a large star dying at some point. Okay, so well done for making it this far. Hopefully that's helped. And I'll see you in the next one.
Okay, so well done for making it to the end. Thanks for watching it. I know some of these are pretty long. And like I said, if they help, leave us a comment. If they don't help, leave a comment. If you'd rather the review bits, which make them really long, I'll put in separate videos. Again, let me know. It's not a difficult job to do, and I can put them in separate videos rather than putting them in the main video, and it will make basically 2 shorter videos. Please like, please subscribe, and hopefully they help with your qualifications.